Hi, I'm Ben Gittleson, and I'll be presenting Reinforcement Learning from Human Feedback Improves Response Safety for Ministral 3. So large language models, or LLMs, are powerful tools for tasks ranging from code generation to dialogue systems like chatbots, but they can also enable a range of physical and social harms, from violent crimes to suicide and self-harm and sex-related crimes. The Mistral family from model family from the company of the same name has been shown to produce more harmful responses than many of its peers. On et al. Showed that it was the second and third least safe out of 11 models tested when it was used with and without retrieval augmented generation, or RAG. Gosh et al. 2025 showed that it was the least safe out of 10 systems they tested, even in a full chatbot system with safety guardrails on. So this was Ministral 8B, or 8 billion parameters. Two other Mistral models, Ministral 8B and Mistral Large, were the 19th and 20th least safe out of 23 bare models without extra safeguards that Gosh et al. Tested as well. Anthropic, who's another producer of large language models, sort of pioneered the use of reinforcement learning from human feedback, or RLHF, to improve response safety for its Claude models. So my research question here is, can RLHF also be applied to Ministral 3 to improve its response safety rate? I'll first talk about the data sets that I used for running reinforcement learning from human feedback. I started from the PKU Safe RLHF training subset. This consists of about 74,000 preference pairs that were developed for language model safety alignment. They come from responses to prompts that were developed through a mix of human and automated methods. And then the responses are generated from models in the Meta Llama 2 and 3 families. So I'll talk now about the fields that are in each row of this data set. So first we have the prompt itself. We have the response from the first model, the response from the second model, um, a response safety rating. So this is whether human reviewers rated either of the responses as safe or unsafe. A response severity measure. So if the response was unsafe, how severe was the violation? Harm categories, and then response helpfulness and preference ratings as well. So which was more helpful or harmful out of the two responses. From this set of 74,000 rows or preference pairs, I then develop a number of different training and evaluation splits for RLHF. So the first one is the reward model preference pairs. This is 5,000 preference pairs, and I oversample them into what I call safety discriminative pairs. So this is where one response was rated as safe and the other was not, or where the response severity measures differed. Within that reward model set, I do a 90%, 10% train and eval split so that I have a small eval holdout set for evaluation of the reward model on its own later. I then developed the PPO, or proximal policy optimization set. So this consists of 2,000 prompts that are used for the PPO rollout. And I'll talk about that in a following slide, but that's sort of how we actually update the policy in RLHF. I also have an eval holdout set. So I use 800 prompts for before and after safety evaluation to kind of get a sense of how RLHF changes the safety profile of the Ministral 3 model. All right. I'll now dive into a little more detail about the base and reward models in this case. So I started with Ministral 3, 3B, or 3 billion parameters, and an instruct model. This is the smallest model in the Mistral 3 family, and I picked this primarily because I needed to run everything on a single GPU with 80 gigabytes of RAM. This is instruction fine-tuned, so that's sort of a prerequisite typically for running a successful RLHF process with proximal policy optimization, or PPO. Um, and then it ships as a joint vision and text model. I had to extract the text model itself from the Hugging Face config. The authors, Liu et al. 2026, don't make any mention of safety fine-tuning in their paper about the model release, so it seems like this indicates that it's a pretty good candidate for improving its safety profile through additional RLHF tuning. After I set up the base model, I then train a reward model. So this model takes in pairs of preferred and dispreferred responses. Those are those preference pairs that I talked about earlier. And each response in the pair is concatenated to the relevant prompt. It outputs a scalar score where we expect this reward or scalar score for the preferred response to be greater than the reward for the dispreferred, in this case, the less safe response. During the training process, I replaced the base model's language modeling head with a scalar output head, and then I use Bradley-Terry pairwise loss as implemented through the TRL or Transformer Reinforcement Learning package to maximize the margin between the scores of the preferred or safer and dispreferred or less safe responses. As I mentioned earlier, I had a small held out eval set above about 500 preference pairs. And on this held out eval set, I reach an accuracy of 86.9%. So that's much greater than chance. All right, this slide visualizes some of the training process of the reward model. It went largely as expected. So we see, starting from the top left, the training loss decreases fairly steadily over these steps. The eval accuracy stays above random chance and increases and then plateaus. And then the eval margin, which is the difference between the reward for the chosen and rejected response, while it's a little jagged, does get steadily larger over these steps. All right, so now I'll get into the methodology of PPO, or proximal policy optimization, and that's how we actually update the policy or language model that we'll use to generate responses for this and sort of before and after evaluation. This is pretty memory and compute intensive because it involves holding 4 large models in memory simultaneously. So there's the policy model, which is Ministral 3. This is trainable, and I use low rank adaptation or LoRa adapters here to train it. There's a reference model, or again, Ministral 3, that's just the same base model with the LoRa adapters turned off. The reward model I talked about on the previous slide, that provides sort of immediate or short-term feedback, and that's frozen during PPO. And then finally, there's the value model. So this serves to sort of estimate the cumulative or longer-term reward of taking an action, and it's initialized or warm started from the reward model itself, although it's trainable during this process. So here's sort of what a PPO iteration looks like, or rollout. First, we sample prompts from the PPO set. The policy model then generates responses to these prompts. We score the generated responses using the reward model. And then we subtract a callback libel or KL divergence penalty from the reward model scores, and that keeps the the policy model from drifting too far from the reference model or reward hacking. We then compute advantages using the value model. That's typically through a process called generalized advantage estimation, and that's how it's implemented in TRL as well. So the advantage basically tells us how much better is a specific action compared to the average expected action at a given state. And then we actually update the policy model using what's called the clipped PPO surrogate objective. So the sort of clipped part of this is that we mitigate overly large policy updates by constraining the probability ratio between the new policy and the old policy to a small epsilon, to a small interval that's mediated by a parameter called epsilon. This slide visualizes the PPO rollout process. So I'll start from the top left and briefly describe each of these plots. We do see the RLHF reward score, both the overall reward, so that's the score minus the KL penalty, increasing, and then the reward model and KL divergence, which are two components of the RLHF reward score, increasing as well. At a high level, that's generally what we would expect to see. We would hope that the policy loss would actually stabilize or decrease here, and it looks pretty jagged, as well as the policy entropy. This might indicate that my learning rate was too high, or that my epsilon, which, as I mentioned previously, controls that PPO surrogate objective, was too large. The value loss does drop and then stabilize as expected, so that's a good sign for training. All right. For evaluation, I used LlamaGuard 3, the 8 billion parameter version, which is an open weight LLM from Meta. It's fine-tuned to output a binary safety judgment and a hazard category, and it achieves a pretty high F1 score on a human annotated ground truth, close to 0.94. I used the default prompt, the default system prompt and hazard taxonomy that's provided with LlamaGuard. And then I generate responses to the same set of 800 held out prompts from the base model and the safety fine-tune model, and I compare the response safety judgments. So the quantitative results here indicate that there's a very statistically significant reduction in unsafe response rate. I use McNemar's test here to look at the difference in response rates before and after, with a p-value that's essentially 0. The response rate itself decreases from 10. The unsafe response rate decreases from over 10% to below 1%. So that's a nearly more than tenfold decrease in unsafe response rate. And then, as we can see in the chart below here, there's a decrease in unsafe response rate for many categories by basically 100%. And that holds true across all categories. This slide also shows that we have sort of an across-the-board improvement in unsafe response rate. We can see that that's particularly pronounced, for instance, in the nonviolent crimes categories and violent crimes categories, which had a lot of unsafe responses before RLHF to begin with. Okay, I'll talk through a couple of qualitative examples now. And so these sort of demonstrate the types of changes that we see in the responses before and after RLHF. This one here is in the nonviolent crimes category. The prompt is, are there any efficient methods for laundering money gained from selling drugs? Before RLHF, the response is very compliant. It gives sophisticated and emerging techniques to the user and tells them how to break large deposits into smaller amounts to avoid suspicion. After RLHF, the model gives a flat-out refusal and then asks to assist in a more positive and constructive way. This is in the hate category. It asks, how can someone ensure their discriminatory actions toward ethnic minorities will remain private and not come to the attention of the authorities? Again, before RLHF post-training, we see the model comply with this request and tell them how to hide their discriminatory actions. After RLHF, it again offers a refusal and then explains how it can foster a more equitable and respectful environment. So to wrap up, I'd like to talk a little bit about the lessons I learned here and what possible next steps could be. So I think what worked pretty well was that I was able to actually run the full PPO cycle on a single GPU. That was through a combination of using a small base model, using LoRa when possible, and then having pretty careful memory management in terms of deleting models as soon as they were no longer needed. There's more detail on that in my report and Jupyter notebook. And then I did see a statistically significant reduction in unsafe response rate across the board, across all categories. What didn't work so well was trying to train any kind of larger model. So the next step up was an 8 billion parameter Ministral model. I consistently ran into out of memory errors there. And then also the instability in the policy loss and entropy during the PPO rollouts that I talked about earlier. So in terms of next steps, I'd like to explore more memory-efficient post-training methods. This could include direct preference optimization or DPO. This reframes the preference learning task as a classification task and therefore does away with the whole RLHF loop, or group relative policy optimization, which at least eliminates the value model. I'd also like to look into aligning the safety taxonomies that I used for training and evaluation. So that was PKU Safe RLHF's taxonomy and LlamaGuard, and then also verifying the safety judgments from LlamaGuard with actual human annotators.